Now let's introduce some more terminology, and this is very important terminology that will follow you through the rest of this course, and if you keep doing statistics on and on. It's very crucial to the idea of statistical thinking. So first of all, the distribution of a variable is a table, graph, or formula that identifies the variable values and frequencies for all the elements in the data set. So we've already been looking at all kinds of tables and graphs. You could also have a formula that show us the variable values and the frequencies. But what we haven't thought about before is the symmetry of such a picture. An image has symmetry if there's a line that splits the image in half so that one side is the mirror image of the other. For example, I think the last example that we did was very nearly symmetric if you looked at this stem and leaf plot for the exam scores. If you think about a line, an imaginary line, cutting through here, it's almost symmetric on both sides in terms of the numbers in the columns. The dot plot also looks close to symmetric. If you look at a different picture, you can still see what's pretty close to symmetry. So it does depend a little bit here on how it's displayed, but you can see that we have pretty close to symmetric data. But that's not often the case. So often you'll have data that there's more data on one side of that imaginary line. So if the tail on the right is longer and most of the data is on the left, we say the distribution is right skewed. Similarly, if the tail on the left is longer, we'll say the distribution is left skewed. So let's look at a picture so it's clear what we mean by the tail. So here's a distribution. And it looks like we're seeing quiz scores. And these quiz scores range from about 33 to about 49. The first question is just which score occurred with the greatest frequency? So because this is a distribution, and for every value of the variable, we see its frequency in terms of the bar, the tallest bar is going to give us the value that occurred most often. So it looks like the tallest bar is this one here. And I can kind of trace it back to see this looks like it should be 46, then 47, then 49. So 46 is the value that occurred most often. It also asks which score occurred with the lowest frequency. So again, we're between 33 and 49. I think this one, which looks like 35, if this is 34 and this is 36. So I think 35 looks like possibly no one made that score at all, or if they did, it's just a few people, because the bar is so tiny you can hardly see it. So I'd say 35, because it has the smallest bar, should be the score with the lowest frequency. The highest score, as I said, 49. It looks like. And the lowest score appears to be 33. Now here's where we want to talk about the shape of the distribution. So the question is this data symmetric? Is it skewed left or is it skewed right? So these are our choices. Symmetric, we said, would be if you can draw an imaginary line and the picture on the left side is equal to the picture on the right side, or pretty much identical, equivalent to the picture on the right side. So it looks to me like no matter what line I draw, I don't get that. For example, this line I drew here at 46, I have a way longer tail on the left side than I do on the right side. On the right side, it sort of just tapers off. So no matter where I drew such a line, I don't have a picture that's the same on both sides. But what did I say? I said I have this tail, a long tail on the left, and our previous slide told us that if we have a longer tail on the left than on the right, we say that it's left skewed or skewed left. So I would say that this is skewed left or left skewed. So one important thing to notice here is that it's not necessarily about which side has more of the data, because more of the data is actually on the right side in this picture, but it's just this tail. The tail is longer on the left, so it's skewed left or left skewed. All right, we'll do one last example. I want to show you what is called a back-to-back stem and leaf plot. So we know how to do a stem and leaf plot, but you can actually do a stem and leaf plot where you have two categories. So for example, here the question is about Academy Award winners, and the data that we're given represents the ages on the ceremony date of the Academy Awards that the winners were when they won Best Actor and Best Actress. So on the night of the ceremony, how old were you if you won the Best Actor or the Best Actress? And they collected this data for 33 years between 1977 and 2009. Now we saw in the previous example when we did a stem and leaf plot, it really helps to have this data in numerical order. So unfortunately this data is not in numerical order. The first thing that we're going to have to do is rewrite it. So I'm going to start with the males. I want to see what is the youngest age of a male winning Best Actor during this period, and the smallest number that I see is 29. So I'm going to start with that and go up. So 29, then I have 30, and then I don't see anyone else who was 30. I see 32. So let's say this is the next age. If we miss one, we can just squeeze it in, because I'm not making my stem and leaf plot yet. I'm just reordering my data. So after 32, I see 36. Two people who were 36. Here and here. And then I see 37. 3 of them. I see 2 people were 38. And then I have 1 person who was 39. And I see 40. I have at least 2. Let's see, 40, 40. And then I don't see 41, but I see 42. Here and here. And what about, here's 43. I have 2 people who were 43. And I see 45 two people. Then 46, 47, and 48. All right, then I see 50, 51, and 52. 53 and 54, and here's a 45 I missed. So let's just add 45 over here. Missed that one. So 53 and 54. And then, don't see any other 50s. I have 60, 60, 62, and 76. So now let me just count to make sure I have the right number. 1, 2, 3, 4, 5, 6, 12, 19, 25, 33. Okay, good. I should have 33. We're going to do the same thing for the women. So again, I want to find the youngest, and the youngest one I see is 21. So I'm going to write that down and go up from there. So after 21, I see 25, 26, 26. And as before, if I miss any, I can just squeeze it in. It's not a big deal. Then I see 28 and 29. And 29. Okay. Then women in their 30s, I have 30. Then I see 31. $32, a couple of them at least. 1, 2. 33, I see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then 35 is the next one that I see. Nope, here's 34. Then 2 35s. And what else? 36. And 38. And I have 39. All right. What about women who are in their 40s? I see 41 and another 41. Then I see 42 and 45. 49 and 49. Then I have 61, 61, 74, and 80. So again, I want to check if I have 33 of these. 1, 2, 3, 4, 5, 6, 7, 14, 21, 28, 29, 30, 31, 32, 33. Good. So now I have everything in order. I'm ready to construct what's called a back-to-back stem and leaf plot. So what I'm going to do is I'm going to have a stem and leaf plot for the age of the females and a stem and leaf plot for the age of the males. And I'm just going to put them together so that they're back to back. So the stems are still going to be here in the center, but the leaves are going to be going out on each side. So we're going to do one per decade. So we have actors and actresses in their 20s, 30s, 40s, 50s, 60s, 70s, and 80s. So this is going to be 20s, 30s, 40s, 50s, 60s, 70s, 80s. And for the females, we just create like we would a normal stem and leaf plot. So here's 21, 25, 26, 26, 28, 29, 29, then 30, 31, 32, 32, 33, 33, 33, couple more 33s, 34, 35, 35, 36, 38, 39, 41, 41, 42, 45, 45, 49, 49, 61, 61, 74, and 80. And then for the data for the males, the only twist is that we're going to start from the outside, start from the inside and work out. So 29, our 9 will go here. Then when we do 30, 32, 32, we're going to go from the inside out. 30, 32, 32, 36, 36, 37, 37, 37, 38, 38, 39. So it's going to be 7, 7, 7, 8, 8, and 9, I think. Let's check again. 3 37s, 2 38s, and 1 39, right? Okay. Then best actors in their 40s. We have 40, 40, 42, 42, 43, 43. So 40, 40, 42, 42, 43, 43. 45, 45, 45, 46, 47, 48. So 5, 5, 5, 6, 7, 8. Then 50, 51, 52, 53, and 54. So we have 50, 51, 52, 53, 54. 60, 60, 62. 60, 60, 62. And 76. So this is our back-to-back stem and leaf plot for Best Actor versus Best Actress from 1977 to 2009. Then part B of the question asks us to compare the populations, and what can we conclude? So because we have all of the data displayed in one image, it's pretty nice to compare the two. So the first thing I would see is that both populations are skewed right. Because we have this longer tail on the right than on the left. And the way I might interpret that is that you're more likely to win Best Actor or Best Actress when you're younger than when you're older. But for the difference between males and females, it actually looks like females are winning it even younger, and then they really start to drop off after they turn 50. Whereas you can see several males have won it in their 50s. But again, you have females start to win it again later in life. So maybe best actors are in their 30s, 40s, or 50s. Whereas best actresses are in their 20s, 30s, or 40s. You can see that for the Best Actress Award, several women in their 20s have won it, whereas the youngest man who won it was 29 and there was only one. But not as many in their 40s, although there were several in their 40s as well, and none in the 50s. So I think this would be enough of a conclusion to draw.